Okay, welcome everybody. So today I'm going to implement a type checker inference algorithm for the functional language that we've implemented the last couple of times. And let's just get started. So let me share my screen. Okie dokie. So basically we had this small language, which is basically the lambda calculus in flow syntax, an expression-based language, untyped at the moment with a simple interpreter. And what we want to do is want to add type inference to it. So the first thing we're going to do is that we're going to define what is a type. So let's call it a p-type. And let's just write up the different types we have in this language. I believe, did we have strings? I don't remember. We can see it in the expression language. We do have strings. Yeah, so we have strings as well. P-type string. I believe these are the values, Boolean array values and lambdas. Yes. Okay. So all of these guys are pretty simple. Whoops. So an array has a type for the elements inside, and a function has archetypes. That's an array of these guys, and it has a return type, which is a type like this. Okay, so this is the basic type system. Now, what does typing mean? Well, what it means is that we have this AST, and what we want is that we want to infer, for instance, the let binding. What is the type of each variable? What is the type of each construct in this language? Okay, so basically what we're going to do is that we're going to make a new expression, which we call T expression. And here we're just going to make them all typed. Well, these guys are the same. Well, okay, let's just do it like this, just to keep it simple. I could reuse some of these elements if I wanted to, but for now I'm just going to do this. And then maybe I should do a search replace here, but okay. Let's see if I get them all. Okay, so that's a copy of the other one just with a different name. And now what we do is that we annotate it with a type. So in this case, we're just going to import the types. So here we need to find out what the type of the values are inside the array. And the same thing for the let. What is the type of this let in itself? In fact, the type of the let is the same as the body. And in fact, up here, it's the same thing, except if the array is empty, then we do need to have a type. The var here, we have to have a type for this guy. Did I call it T-type? I did. For the if, the type also here. So we're just going to add a type here for each of these guys. Okay. So what did I do wrong here? And is it not called type? Gringo pflow type, like that. And then did I call it something else? I'll call it p-type. Okay, let's just call it p-type then. Okay, so now we have the AST where we can kind of like put in the types everywhere. So the way type inference work is that let's just do type checker. So a type checker is, well, I'm going to say type check, and we're going to give it a expression, and we're basically going to give it a T expression out. That's basically the idea, right? So let's just include the different parts. And for now, I'm just gonna say T bool false. Okay, so our goal is to implement this guy. Let's just hook it up so we call it immediately. So we'll just say we have the program here and we're gonna type check it. Okay. So now the basic plumbing is in place. So, and for now, we can just add a print of this guy and we don't need the interpreter for now. And if we run this, oh, what's wrong? What did I do wrong? Yeah. If you run this, it's just gonna print false, obviously, because we didn't implement it. Okay, so to do a type, so basically we have to do type inference. So basically we need to do, what we're gonna do is that we're gonna make a type environment. Type environment. That's a structure which we'll be filling out in a moment. So what we're gonna get is a type environment, and we're gonna get a p expression, and then we're gonna type check that and tell us what type that element is. Okay? So we need to implement this guy. I didn't call it T-type, I call it P-type. That's gonna confuse me. Maybe I should rename it. I don't know. What do you think? I'll rename it because I'm gonna make that mistake again and again and again. And in some sense, it's more logical to call it T. And then we call these guys with a T instead. So it's like P for parsing, T for typed, right? That makes sense. Let's just change them so it's more consistent. Otherwise, I'll be confused again here. And then here, this guy, that's fine. And that's going to be a T type. Okay. So to do this, we basically have to implement this function. So let's just do that. So the first thing here, well, this is easy. That's a T-type bool, right? So some of them are easy. Okay, so here, what is this type? Well, what is the type of the values? And now the tricky part comes. All of these guys have to be the same type, right? And what about the empty case? What is the gonna type be there? We don't know, right? If we have an empty array, what is the type inside? So the way to do this, introduce type variables. So that's the next thing we're gonna do. We're gonna introduce a type variable. And a type variable is basically just a placeholder for a type. We don't know what is yet. Okay. So we call these type variables, and they just come with a number to identify which one it is. Okay. And now, in fact, we have the toolbars here. This is a environment where we can define what the type variables are. And what we need to be able to do is to make a type variable given an environment. Then we want a type out. And to do that, we need to have a unique ID. And that has to be mutable in that sense. So to construct a new type variable, we're just going to say the ID is dereferencing the unique pointer. And then we got to increment it so that the next call will get a new type variable. Okay. So yes, this is imperative code with side effects, but in this case, it's a well-known pattern. When you need to do a new ID, that's a useful way to do it. Okay, so basically what happens is that here, we're gonna make a type variable. We're gonna say the array type is this thing, okay? And then we gotta do something with these guys, but but before I get to that, I'll just say, what is the result? Well, it's this. It's a T-type array of whatever type is in here, okay? And then the point is that to get the final type, what we do is that we do what is called unification. So to unify, we'll fold the variables instead, the values, And then we're going to say the value type. We're going to type check that of the value with the environment. And then we're going to unify types. Then we're going to unify these two types. What does that mean? I'll get to that in a moment. But the entire thing, the entire idea is that we have an array of a bunch of values inside. We don't know what the type of that those values is, so we make a type variable. Then we go over each of the values in the array and get that type, and then we say it has to be the same as this type, right? So we basically, all the types inside the array, they have to be unified, okay? So that's what that is. So what is unification? It takes a left type and a right type and have to make sure that these guys are the same. Okay, so we'll implement this in a moment. For now, it's just like that. And no, we can make it return it. It shouldn't be we can do this. We don't have to do a fold. We can do an iter and just say all of them have to be unified against the A type. That's fine. It doesn't have to return anything. Okay. So for now, before we get any further, let's just implement. Let's just make a type variable for these guys. For the rest. Now we'll do a to do. That's a good pattern. To do. So we don't have them implemented yet. We'll just add to do for each of these for now. And then to do, what is to do going to do? It's going to say type check to do to string of p, and until it's done, we're just going to make a type variable. Okay, and let's fix everything so it compiles. And make type variable once the environment. That's fine. What else? Iter. Okay, we don't want the ACC here. That's wrong. All right. So to implement this guy, basically, it's gonna be, let's just do a part of it. These guys take P's and convert it to the corresponding thing. This one is easy. These guys are, oops, yeah. So here we need to find the type of this guy. So what we can do is that we can just call the type function for each of these guys. What is the type? It's this guy of the environment and then E. So we'll change this to also take a type environment at first. And then we'll make a type environment function just to get ready for that guy. And that's going to be simple. It's a tree. And then it's an integer like that. Okay, so this guy will do a rec function. That's going to be helpful. So this guy is a T array value, map values, and then it's the type. Right? T lambda args is the same, rec body, and the type. T let ID rec value.
You missed rec variable in the line number 24.
Yes.
Map second argument.
Yes. All right. Thanks. T var ID type. T if rec cont rec then rec else type. T call rec fn map args rec type. T array map values rec type. So it's, you can see the code is simple, but simple is good. Okay, let's see if this compiles. T llama. We want the lambda. What did I do wrong here? we want, okay, so this guy needs values inside. Yeah. Okay, so what we can do is we can take value, that one that does values, and split that out. And then it gives a t value like that. And it's basically the same just for a subset of these guys, which are the values. And it's not this guy, but whoa, this guy instead. I think that should work. And here we're just going to say p value, then it's this guy instead. Okay, but the lambda here is wrong. Some of these is this guy. Here, it's this one, it's not. Is that correct? Yeah, that seems correct. Okay, so let's just try to run this and see what we get. I need to give it 2 arguments. We gotta get the typing environment, make type environment, and we're gonna give it to this guy, okay? So here, there you go. Now it says to do blah, 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 a bunch of stuff we didn't implement. But we did implement the array. So let's do a simple test of array, this guy maybe. Let's do that one. Array instead. So here, it needs, we don't have the call. Okay, it's because there is a call. Let's just do a very simple array, the most minimal case first. So here, okay, we don't type check array. It's not an array value, it's an array. So let's do that. Let's add that guy. It's similar to the value. We could maybe make a function, but like that. And let's try that. So to do, which to do is it? To do unified types. Okay, yep. So basically, let's just add a print of what this is. To do unify to string left, right. Let's just do it like that, just to validate that that's what we're seeing. Okay, so now what you can see is that what it does is that it constructed the type R0 for the array type, and then it unifies it against the type of the first element, which is in this case an integer, and then again for the other 2 guys. And the resulting type of our array is then a type of this type variable. Okay, so what does this mean when we have this guy? Well, what it means is that this type variable 0, we know now that it's an integer. Okay, so basically unification is like this. We're gonna implement this guy, and we say if we meet a variable here on the left hand side, then we'll do something. Otherwise we'll do like this. Okay, so what should happen here? Now we have this is 0 in this case, and we get an int on the right hand side. So basically the idea is to update the type environment and say that this type variable is an int. See the idea? So, and we'll just do that using side effects. So we'll change this tree to be a ref instead. That's fine for our purposes. You could do it in a functional way, but this is okay. So the first thing we got to do is that we have to see if there is an existing type for this guy. Environment tyvars. If there is one in advance, we don't want to just update it without knowing if it's the same. So if there is a type, we have to do something. If not, then we'll just say these 2 guys are the same. Okay. So this is we'll just update it with that value. Okay. And here, then we'll say if this type is equal to that type, then we're all good. Otherwise, we have a type problem. We'll just do toString for now. Left is not compatible with toString right. Okay. We can simplify this. Just do it like this. Okay, so now, hopefully when we run it, we'll know that it doesn't have a to-do, but this type is not resolved. That's what we call it. It didn't resolve it in the final program. So what we'll do is that up here, when we convert these guys, when we get the type out, where was it? Up here, When we get the type out, we'll resolve the type. Resolve type using the environment. What does that mean? I'll explain that in a minute. But basically, it means that, no, we'll not, okay, now we have a problem. In fact, the phasing is wrong. Let me just think about it for a moment, because right now we're doing type checking and then finding the type immediately. But in fact, it could be that it has to be done later. Because of unification, we might not know the type until all of the rest of the program has been typed. So we should do it at the end instead. So we got to do all the recursive calls before we resolve the type. So one way to do it is that we can resolve a T expression with an environment. That's one hackish way to do it, but let's just do it like that for now. So basically this one will map and resolve the types. So let's just do it like that. These guys are already solved. This guy is, so we'll just say resolve on the type. So we're going to do a recursion on the body. I forgot that up there, and we're going to resolve this one. This is not the most elegant way to do it, but okay. That's fine. And so let's just define rec. It's going to be T resolve and like that. Okay, and then resolve is takes a type and resolve type, which we didn't implement yet, but which we will. Okay. So when you have a functional transform like this, where you take a value and return a new value, it can seem wasteful in some sense that you're reconstructing everything from scratch, but it's just a very nice interface semantically that you understand what's going on, and it's easy to get it correct. And the thing about is a compiler or a type checker like this is that it's hard to get it right. So you want to have code which may not be efficient, but at least it's correct. That's the way to think about it at first, and then you can always optimize it later. Because the hard part about a type inference type checker is to get it right. All right, what does resolve type mean? Well, it means that we will resolve type variables. I could make a rec here again, but okay. And here, that's the juice. So what we're going to do is that we're going to look up in our type environment vars on ID and return that type. And if there is no such type, we'll just return the type variable as it is. Okay. So let's fix all the mistakes. Type. We'll call it array type. What else? Call to resolve. We need 2 arguments. That's true. We need the environment. What did I do wrong here? Type function map. We need an end parenthesis here. Lookup tree. Yes, it's a reference. So we gotta dereference it like that. T expression needs to be inside value. So it's the same thing again. We gotta do a resolve values as before. O, and here it's resolved T value, except for this one, which is resolved T expression. Like that. Okay. So I guess we gotta call the resolve function as well. We didn't do it. So it's here, and let's plug it in. So we have that, and then we resolve the type and see if we now get array of int. That's the goal. Let's see if that works. Oh my, it does work. Okay, good. Now, we have a bunch of to-dos we didn't implement, so let's maybe go for the factorial program again and see what it is we are missing. So basically the way to do it is to just implement these constructs, and then let's see what happens. There are surprises to come, but we'll get to those in a minute. Let's just get these guys implemented one by one. So it wants let. How do we type let? So we have a value type, which we'll just find by recursively calling this guy, type check p expression environment on the value. And we have a body. Okay, so the body type, that's the type of the body. But what about this ID? What are we going to do about that? Well, the thing about it is that we'll just extend the type environment with IDs and their types. So we'll just say vars, what is their type? From a string to a type. Okay, so that's what let does. It basically adds this guy. I'll move this one up to be close to the make function. That's easier to control. Like that. So basically our type environment has the type of local variables. So here, what we'll need to do is that we'll make a new environment here, which is a type environment, but with the vars. Did I call it vars? Yes, I did. Where the body, where the type of ID is value t. Okay. And then that's the type of let. And that means here, what is the type of this guy? Well, we look it up in the environment. And if we have it, oh, that's the type of variable. Otherwise, it's a mistake, unknown ID. And we have to return something here, so we'll just make a type variable in that case, okay? Set tree needs 3 arguments, that's true. That's it. Okay, let's see if we get a little bit further now. And it says we don't have a type checking for lambda. Okay, let's do that one then. Lambda, where is lambda? It's here. What is the type of lambda? So we have a bunch of arguments to this function, but we don't know what their names are, but they will respond, they correspond to local variables, okay? So the way to do it is that we're gonna fold these guys, and then we're gonna make a type variable for each of the variables. We don't know what the type is. So it's basically like this. What is the value of this? What is the type of this argument? We don't know, so we'll make a type variable like that. So now we've constructed an environment where we set up a type variable for all the arguments to the function, and then we'll just type check the body in that. Okay. So it needs sequence as well. So let's do a sequence. What is the type of a sequence? No, we don't need the, I think at some point we decided that it was a bool if it was the empty sequence. But other than that, it's just the type of the final element. So we'll just do like this. So what did I do wrong? expected one argument to type bool. Really? Oh, it's type bool. It's not bool. It's type bool. There you go. Okay. So let's see what else. If, all right, let's do if. What is an if? So type of the condition will recursively evaluate that. And we know the condition has to be a bool. So how do we express that? Anyone knows? The way to do it is we just unify it with a t-type bool. Now we unify these guys, and that's the way to say that this type has to be a bool. And then we have a then type, and we have an else type. And the thing is that these two guys have to be the same as well. So we unify these types. Basically saying that the then and else branch, they have to give the same type. And then we can use the then type as the final type of the if. That's going to be fine. Okie dokie. What else? Call. So call. Okay. So what about a call? So we got to get the type of the function. Okay. And then we got to get the type of the arguments. So let's find the type of all arguments. Okay. And then, so then we have a call type, which is type function. We have we know the arguments of the types, but we don't know the argument of the return value. So we're just gonna make type variable for that. Okay. And then we say that this type here has to be the same as this one. So we just unify these guys. Okay. And what is the return? What is the resulting type? Well, in fact, it's this type variable. That's the return result type. So we'll put that as a variable here and say that is the type of the call, right? So that's how you do typing of a call. Okay. So now it says unknown ID. We have a bunch of IDs it doesn't know. So we got to figure that out. So some calls, it's similar to in the interpreter. So if you remember in the interpreter, we had these guys handle built-in calls that we did in the call case. So basically, we need to have the types of a bunch of known calls. So what we're going to do is that we're going to say, we're just going to do it like this, ID, and then default none. So I'm going to say that if it's a built-in function, we might know the type already. Otherwise, let's handle it with the other code. So I'm just going to do it like this. And if it is handled, then the value is this. Otherwise, it's this code here. Okie dokie. In fact, this one, we can do it like this. It's the type of the function. We can do it like this instead. That's even more clear. Okay, so it's in here. Type built-in ID. So let's do it like this. If we have a built-in, then that's the type we're going to give. Otherwise, we're going to do it like this. We're going to just figure out what the name is. Okay. So we got to have the type of the built-in operators. Okay. So for now, let's do pairs to tree. And it's our old friend. And then let's, you know what? Maybe we'll just grab the one from the interpreter. It has these guys here. So let's just grab all of these guys, and then we'll do the types for each of these guys. So it's going to be, I don't think we need the peep. We'll just do the name. I could have done it the other way. All right. We can do it like that. We'll have to write something else here. Let's just get rid of this and figure this out. Okay. I'll explain why I'm going to do a function in a moment. But these are the built-ins. Whoops. And the type built-in is not a type, it's a maybe type. Maybe we know the type of this guy. And then we're just going to look up tree. Built-ins, ID. And maybe we get a function. If we do, we're going to call that function to return the type. Otherwise, we're going to return none. So this needs to return a type. So what is negate? Let's just do this one as an example. It's a type function that takes an int and returns an int. You see the idea? That's what that is. So maybe we'll just comment these out until we have those that are needed for the fact program. Okay, what is the type of less than? Well, let's figure it out. At least it takes a bool at the end. That's we know. But what are the arguments? Well, they have to be the same, right? So the way to do that is to make a type var. So we'll make a type variable, and we're going to say it's the same type variable for both of them, right? So it means we need to provide the environment here. So let's see if we can get this to type. I guess we can just comment stuff out until it does, until we can run it. And built-in returns, return from switch. Oh, it should be sum if we get it. So that's why we have to use a function, because each time we have a comparison, it can be a new type. So we need to make a new variable, type variable for it. That's why we use a function, so that it's constructing a new type variable every time we have it. Okay, let's just run this and see what happens. Okay, so we have unknown how to unify, we have minus, and we have fact, and we have star. So let's just do them one by one. In fact, this one is the same for all comparisons, right? So we can just, let's just say that's a comparison. It's this guy. So we can do it like this. And this one is all of those four guys are int, binary int. So let's just call it int. And we can say it's the type function that takes t-type int and an int.
Couldn't we add strings, for example?
No, not in this variation. I decided it's not overloaded in that case. In this language, we cannot add strings. Just to keep it simple, because it's a little more complicated. So I'm just going to ignore that for now. Index, it takes, okay, this one is interesting as well. So let me try to write it up. So it's a type array of something, and then it's a type of an integer, and then it returns something. And now you see why we have these type variables. We know it's the same type. So you can see these type variables are convenient to express that. You have an array of something, and when you index into it, you get that type out, right? This one is easy. It takes a bool and returns a bool. Okay, and I guess we only have the two, these guys here. They're very similar. It takes that they're binary. Okay, so these should be the types of the build-ins. I made some mistake somewhere. Here we gotta end this guy. And what did I do wrong? I need one more parenthesis here. And what does it say? There is a missing parenthesis somewhere else. Up here. Okay. So if we run this now, you can see now we get a bunch of unify function against something. We didn't implement those, and also unknown ID fact. So unknown ID fact, that one surprises me because I think we did implement that, didn't we? Didn't we have a let binding? Maybe I made a mistake. Oh, it's because it's recursive. Yeah. So recursive functions are special. So if you look at fact, so it's a let binding, but inside let we call itself. So in some ML languages, you have recursive let binding for this exact reason. So what we are going to do in this case is that we're just going to make a tyvar for the ID, and then we're going to bind that in this environment. So we're going to make a value environment where we say that ID is this type variable, so we can handle recursion. And then the result, we're going to type the value in that environment, and then we're going to unify those, unify that guy. So that's a way to do it, like that. A little complicated, but I hope that was more or less clear. It didn't help. Fact, still had a problem with fact. Unknown ID fact, unified types, that's fine. Print debugging is always your friend. Here, so it's further down. Okay, so I guess there must be some problem. What could it be? More print debugging. So where was the error? Unknown fact ID. So var here. God damn it, this is too hard to follow. So first we should indent them so we can see what's going on. So we have a let binding, and then we have a sequence with this guy inside. That's the body, isn't it? Another thing we could do to clarify this, which is a useful pattern, is to add a pretty printer. So let's just do that. Pretty print, pretty p expression. So it's easier to see what these guys are. And we have the blueprint, which is very helpful for this. This one is just a recursive descent over all of these guys. Superglue is a great one. If you don't know that one, I will recommend that you learn this guy. It's very helpful. It's like a fold with two string and then it glues it together. So it's like a fold string glue map kind of thing. It's great. And here lambda is going to be these guys and then an arrow and then the expression of the body. So here we're going to do a blueprint, which is also a great one if you don't know this one. So we're going to say it's ID equals value semicolon body like that. And then we define what these guys are. So this one is easy. Value is pretty p expression of the value. So it seems like a strange way to debug the bug I'm trying to find, but it is a useful pattern in general. So very often when you have some problem, it's a good idea to improve basically your debugging machinery. And in this case, having pretty print is so helpful because that will make it so much easier to look at that debug dump that I just presented before, because it's going to be formatted nicely and it's going to make it much simpler to debug my mistakes. So I can only recommend that you, when you're programming, think about these things, and from time to time, okay, can I add some small thing that will make it easier to debug this? Let's just do it like that. All right, 3 to go. We're soon there. Call, that's gonna be fn plus this guy, and then it's a super glue of the arguments. With commas in between, and then it's gonna be one of these guys. Array, we had that already. It's the same as this guy. A sequence is, it's a blueprint. That's the best way to do it. A sequence is one of these guys with the values in here. So what you'll notice in a moment is that the reason why I use super glue and blueprint is that it helps me make the indentation correct. So it's very, very helpful. So what I'll do here is that I'll just do it like that. And I made a spelling mistake somewhere. All right, let's see where it is here. Okay, so we have this guy. So to test it, we're just going to say this program that we just passed, and let's just print that. And you see now the pretty print comes out with indentation and everything, which is very helpful, right? Because of blueprint, it is so smart that it knows how to indent everything just from this template I have here. When I have this indentation, it understands what it needs to do. So that's very helpful. And now, hopefully, it should be easier to figure out what's going wrong in my type checker. So let's go back to the type checker and now print here. Now we're going to not print this guy, but a printed version of it. And hopefully that'll make it a little easier to see what mistake I've made. So let's have a look at it. Now this is probably so long that another useful pattern I do is that I run these programs and then I pipe the output to a file. That's also something I do a lot. P flow, like this, and then I just pipe it to a file called out.flow, and I use the name out.flow because then I get syntax highlighting in here, which is nice. All right, so we had unknown ID somewhere. Wasn't it unknown ID here, fact? So all IDs are unknown. What's going on? So in here, let's see. So we're lambda n, and then this guy, this guy, this guy. That's fine. These guys work. And then fact and fear, fact, and then oh, it's hard to see what's wrong. Unknown ID fact here. So here, it's like we're doing it again. It's the else branch. What's wrong? Right? This is the else branch, and it doesn't know the fact. No, it's not that one. It did complete that one. That's what that is. So it's the call. It's the final call, I believe, isn't it? So what I can do as well is I can print the type environment where we have the mistake. Unknown ID, we'll just print the type environment. Get 3 keys of vars. See what's going on. It knows about n, but it doesn't know about fact. So n, when is n defined in our test? It's inside the body, so it's this fact. So it is in the body of the let. So here, what am I doing wrong? So let's just try to print the vars in this guy, but it wasn't in this call, it was in the body. I'm confused. Let's get rid of this print. So now it has factorial in the environment, and now it has unknown ID. It must be related to this guy. So before body, after body, or is it somewhere else? We'll see. Before body, after body, it's not inside that guy. So it's somewhere else. Okay, so it's not let that's wrong. What could it be then? Could it be lambda? So here, and let's do the end of the lambda. Yeah, it's inside the lambda. Okay, so what did I do wrong here? Oh, you see, it's here. I made the mistake. I have, it's not, I'm not folding over the environment here. ACC. That didn't help, but that was at least one mistake, right? We know it's inside the lambda type checking. It doesn't know fact. So let's print the environment we know here. Oops, dot vars. N, the first lambda, there is another lambda. Why is that? Why are there 2 lambdas? What's going on? Why are there 2 lambdas? So what is that lambda? There should only be 1 lambda. Am I doing something wrong? It's a p sequence of this stuff, all right? And the second time, it's why why is there lambda called 2 times? In fact, it's called 3 times, many times. Okay, so it's somewhere else. Maybe, what is the top level? Did I do something wrong in the sequence, for instance? I don't know. Okay, so we'll do something else here. We'll just say, instead of the entire thing, we'll just give it the struct name to see what's going on. Let var, very strange, lambda here, because let lambda and then sequence. And then it does it the entire thing again. Why? So when we have the lambda for the second time, why is that? So to get the call stack to work, I'm going to call the same program with no JIT. Then the call stack will have line numbers. So 77, so it's from a lambda, and then it's 28. Type check P expression here. So we call it here. And what is the first call site? 88. Oh, I know what it is. It's because we recall type recursively, and we shouldn't, right? So we mixed it up. It's because we got to call this guy once only for the entire program and then convert it afterwards. Because this one basically constructs the types for the entire program. It recursively goes through all of the program and gives you the end result of the type. And the problem is that then if we recursively do that for all of them, we'll tap the same thing, but only as in a part of it, which is definitely wrong. So that leads to a different problem, because if recursively do this, that's fine, but we kind of like throw away the types of all the sub-expressions beneath them. So what we need to do is we need to change it so that there is a place we can put those guys in. Okay? So the way to do it is that if you remember this expression here, we have a type in each of these guys. So what we do is that we construct a type variable for each of them, and then we call the type checker, and then we can recursively extract them. Then it'll work. Okay? So, so to validate that we don't have a, so basically for now we'll just do this type check the entire thing, and then how do I do it? Well, I can do it with by just for now to test it. I'm not gonna call this guy recursively. No, I can't, because I need a T type. Annoying. How do I do this? Okay, so one thing we could do, instead of going over P here, we could change it to work over T. Because then there is a type where we can put in the T already. Okay? So the way so right now, if we look at our main flow, so we have, we construct a P expression, then we do type checking and resolve it. But the problem is that we only need to go through the entire thing once and then kind of like put in the types there. But we gotta call recursively these guys. So another way to do it is to change this guy to return T expression. That could also be another way to do it. What's the best way? I think the cleanest way is to make a I think the cleanest way is to change this to okay, we'll do a convert P expression to T expression, which is basically gonna recursively construct a type variable for each of these expressions, and then we're gonna change type check to unify with those type variables. So let me show you what I mean. Okie dokie. So here, and the type here is just going to be a type variable. Okay. And then we got to do the same thing for these guys. Okay. So now we have a function that will construct a placeholder, so to say, for each of these expressions. And then this one will be changed to work on T expressions instead. So we'll change type check to work on these guys. And in fact, I don't think we need this one. It's just this guy down here that will change to be based on T types instead. And then we'll fix that in a moment. And it's going to return a type. So, and it should be called T expression, obviously. And this one is going to call it, well, we can call it P, but these guys are going to be T instead. Let's call it T type. See, that's the idea. So basically, this function will type the array, and then it'll unify the result with the type variable we set up above. I hope that's clear. So let's we need to do that for all of them, but all of the guys that have a type variable inside. But for now, we'll just do it like this and get things to compile. And I hope that should be better. So here, lambda, it has the T type. The next one here, it has a T type. And now, if we don't know it, we already have a type variable, we can just return that instead. That's fine. Like that. The call has a T type and call it, we just unify with that guy as well. this one, in fact, this is not an array, is it? Is it a function? I don't know. I think, in fact, this is a function that returns an array. No, but this is the call of that function. Okay, so it is correct. That's fine. That's correct. Let's call it T-type. And the final one, no, T-type. These two guys. Okay. So what else is wrong here? Fn, it's not a P, T, right? Like that. Okay. So let's see if that helps. So back in this guy, first we're gonna construct our expression with all the type variables. We'll call it T0, and then we're gonna check it with this guy once, and then we're gonna resolve all the variables at the end. So what's wrong? Oh, it's the type we get out here. Okay, that doesn't matter. We'll ignore that. It's still that expression from this guy we'll resolve. Okay, there you go. So we still have the call stack print. We can get rid of that, and let's run it again. And now we don't have the unknown IDs anymore. Instead, we have to-dos for our unification. All right, so the next problem is to implement these guys. So let's just quickly do that. It's not that hard. Where it's in the type checker. Unify, unify, unify. Where are you? Here I am. So let's remove all of these guys and see which cases we miss. We miss these guys. Okay, so if this guy is, so if they are the same type, we are fine, right? Then there's nothing to do. But if we get a bool here, it could be that it's a type variable on the other side, and then we want to unify with that. So we'll just make a function call, right? That does that. Okay. For array, we also want the other side to be an array, but it could have a type variable inside. So let's call it do right here. We'll fix that in a minute. So if we have a, whoops, left type here, we want this guy to be a right type as well, and then these guys have to be the same. This guy and this guy has to be the same. So we unify the children like that. Okay, and in the default case, it might be a type variable. No, in fact, if it's a type variable, we can unify this type variable. No, we can bind it to an array with a type variable inside. So we can make a structure. Type array and make type var inside. So we know that the right is one of these guys, right? And then we can unify with that. And in fact, we can just, if we make the type var here, we don't have to recurse too much. We can do it like this. So the L type is the same as that var, okay? And the rest is an error. So let's make an error function for the rest, okay? So if you have two functions, a function, then it's the same thing. If it's a function, we can unify just like we did up here for each of these corresponding guys. And if they have the same number of arguments, if not, it's an error. Otherwise, we can unify the arguments. And it's safe to do it like this because we know they are the same length. And if it's a type var, then we know, similar to before, that it's a function type. And then we can, it has a return var and it has arg vars. We know it has the same number of arguments as this guy, and we'll make a type variable for each of them. Okay, so it means we know that the right-hand side of it is a type function like this, which is arg var and ret var. We can call them vars here. And then we can unify the left with this new type. And what we also have to do is that we have to unify the type var, this ID, with that new type we constructed. So the right-hand side has to be unified with this guy, and the same above, when we kind of like shell out that type variable, right? Like that. And we need to implement the do right thing. Do right is like if switch, if it's a type var, then we know it's we can do this guy. So maybe the simplest way is just to swap these two guys, right and left. That'll work. Otherwise, it's an error. Okay, an error is we're going to report a type error. Whoops. And we had this guy. Let's just do that. So this is another place where it would have been nice to have the pretty print thing for types. Then we could have a nice error message. But for now, that's going to work. We'll just say error like this. Okay. Unified type. What did I do wrong? It's called unified types with S. Okay. And here, default error. Okay, so now at least it compiles, and let's see what happens. And now type var is not compatible with type int, so we made a mistake somewhere. Because that should be compatible. Oh, it could be it's because it already has a type in here. So this error may be which is, oh, it's because the right, if right is a type variable, then it's not a problem. Now the problem is, I know what the problem is. The problem is that down here, if the right-hand side is a type variable, then we have a type variable against a type variable, and that's a special situation. So we'll save that for a little bit later. But in all other cases, it is like this. So let's do it like this. So type vars are identical. So we'll handle that in a little bit later. Okay. And now it's called left ID. Okay. So if we do this now, let's see what happens. And it says all these guys are identical. And then it has a problem that a type var is not available, comparable with a function. Okay, I know. It's because if we have a function here, it's like the other case we had before. We gotta shell out that. We gotta structure out that function. So we do that by just reversing these guys, and it's the same thing with the value with the array. Okay, so let's get rid of these guys. All right. So now let's try again. And if we run this now, we get all of these guys that they should be identical, these type variables. So the thing about this is that now how it's like, if you look at the environment we have here, what it basically says that whatever entry is in Tuvar's number 19 should be the same as is the number 1. But it has to be that continuously. And the same thing if we go down here, we say, oh, 21 also has to be the same as 19 and number 1. So basically what we're saying is that we're building up equivalence classes. So we need to have a data structure that can represent equivalence classes. And there is such a thing. It's called union find. So we have a data structure called union find here that exactly does that. So you can define that these two elements, they belong in the same equivalence set. So we'll add a union find data structure to our small type checker, and then we can use that to unify these guys. And we have to import it. Okay, so, and in union find, that's what we do in this case where we have Tuvar against Tuvar. Where was it? Here. So what we need to do here is that we're going to say union, that's the name of this guy, and that the left ID and the right ID are identical. That's what we're going to do. And we got to return the type. It doesn't matter which one, we'll just say it's the left-hand side because they're equivalent. Did I do something wrong? Yeah, it's going to return the root. It does, no, what is it? No, it doesn't want to return anything. It's the, it is exactly like this, like this. All right. So now what we've done is that we've recorded that these guys are equivalent, but we haven't really resolved them yet. So what we have to do now is that, let's say that we had number 1 and 7, like these guys, right? And maybe in the Tuvar's tree, we had an entry for 6, or maybe we had one for 1. But the thing is that, as you saw before, we had a sequence where basically it was like a sequence of these guys that were joined up. Now, what union does is that it'll give you the root, which is the parent that represents all of these in this union class. So what we'll have to do is that we'll have to move any Tuvar bindings from this guy to this guy. And the same for if we have any binding for the right-hand side, we have to move them to the root. Okay? So move Tuvar binding. It takes from to, and it needs to say, if we have a type in Tuvar's from, it needs to be transported to the to. Okay? Tuvar's, they are referenced, so we can do that, that's fine. And in fact, we have to check if there is already, it's like this case down here. So the way to do it, instead of doing it like this, is that we'll just unify with that guy. So we know we have the 2 and we have the M type. Okay. Otherwise, there's nothing to do. All right. And the second thing we have to do is that when we resolve our type variables, down here in resolving, we might have a type variable here. We have to find out what that equivalence class is now. So we do that by using union find like this. And then we find out what is the new ID for this guy. And then that's the one we look up. Okay. And when we're done that, then we didn't get any print. Did we have a mistake somewhere? I guess we did. Oh, we have an infinite loop. Yep, that happens. We have a recursive function, so in some sense it's not surprising. And the question is just where we have that loop. So let's think about it. Where could it be? The simple way to make progress is just to add a print after each of these guys. Okay, so let's run that and see how far we get. Here, it's inside here. Okay, so inside this guy, we have a endless recursion. So how could that happen? Okay, it can be in the unifying types, obviously. That's where it is most likely. So in the unifying types, it's probably most likely here we have an infinite recursion. And then let's just print these types and see if we can spot what that is. There you go. So we have a type function against the type var, and these two guys kind of like alternate all the time, it seems. All right, so let's see why that is. So if we have, what is it we have? We have a type variable against the function. So what did we do here? Type variable against the function, and then we reverse them. Great. And then if we have a function against a type variable, what do we do? A function against a type variable, then, oh, okay, so here, this is wrong. It has to do the unification against the type. So we should, maybe we should make a function that does the type, this unification that happens here. That should also happen. Let's move that out to a function instead. So let's say bind tyvar, tyvar type. That's what this one does. Okay, and in the array case here, we should bind this tyvar instead. That's a more clean way to do it. Okay, and the same thing in the function down here. This is a cleaner way to do it. It's going to be the ID and the RT like that. Yes. Okay, let's see if we still have an infinite recursion. No, we don't. Okay, so now we have some type problem. Type function is not compatible with int. Could it be we have a type problem? I don't think so. Let's see here. No, I don't think so. So so now it would be nice to have some better error handling so we could see where the problem is in the source code. So basically positions and stuff like that, because it's kind of hard to figure out where this problem comes from. But we're just gonna approximate it by doing this print. So we'll try to find out where that type problem is. Var, so there's some var. What is the var? So let's do the print in the var. Oh, it's not inside var. Surprising. Wasn't that what it printed? What am I missing? Oh, it could be that it's a, yeah, it's probably indentation. All right, so let's do it like this. So this is kind of like a brute force way of getting the recursive call structure more understandable. So any recursive calls that comes in the body of this guy will be highlighted this way. And then we'll reset the indentation here. Was that what I called it? Semicolon. Okay, so let's try that. That's better. Now we can see what's going on here. So it's in a call, I guess, or could it be if? We gotta have the end of the of them as well. Otherwise, it's too hard to see what is what. So we'll just say like this. So where is the end? So here, int lambda is not, it's after the lambda. So what's before the lambda? It's let. So the let binding has a problem. I guess it's our recursive let that's a problem. So let's see what I did with that guy. Did I do it wrong? So is it correct? No, the lambda was typed and the let, but the let is not typed and the type is not. And then after that, we call, it's the call. Okay. So it seems it is inside let, right? And what are these types? So it would be helpful to be able to print these types. So we're going to add a pretty type printer. And you know what, just to keep it simple, let's just put it in the type checker file because then we don't have to move things around for now. All right. And for this guy, we're going to look up the root union find. And see if we have a type for it in the environment. And if we do, we're gonna pretty print that guy. You normally call these type variables lambdas, so we'll just put it in parentheses to help debug this. Otherwise, we're just going to say it's a lambda, which we don't know what is. Like that. Okay. So super glue, we need this guy and recursive call somewhere. I missed call to expects 2 arguments here. Let's put this on a separate line. And union find needs 2 arguments. Of course, we need to give it the ID. Okay, so we have pretty type now, and then we can add a nicer print what the type is from each of these guys gave. This guy. Let's see if that gives us a little more hints about what's going on. So lambda gave int, so that's definitely wrong. Lambda is not an int, so the typing of lambda seems wrong. What did I do in lambda? Type of t lambda, where is it here? Well, it's not the return type. It's a function, obviously. It's the entire function. So it's just a t type function with the arguments. So we got to keep the arguments up here. It's not enough to fold it. So archetypes, let's do it like that instead. Map arcs. And then we make these guys. Okay, and then we say fold I, and then it's the archetypes I, like that. Okay, and then we have the final type is archetypes return type, like that. Okay, what did I do wrong now? Unknown name I, it's because I need to add I here. Okay, like that. Let's see what happens now. Okie dokie, so now we get an int, strange formatting here. And then it says function is not compatible with function. Let's figure that out. But the first, there was some strange printing. Did I make a mistake in the print? Yeah, you have to have parentheses like here. Okay. Okay, so that helps. So now at least lambda, it gives an integer to an integer. That's correct. And then it says type function is not compatible with type function. So these two functions are not compatible. So why is a function not compatible with a function? So that's our unification of functions. Let's check those guys. Unify, and now we can use the nice pretty printer here. Let's do that, right? Now we have it. Let's just do it like that at first. Let's see. Oh, okay. Okay, so when we bind a type variable, I see what it is. It's because we have a partial binding. So in the type environment, we have a binding with type variables, and that might be compatible. So just because they're not the same, it might be fine. So what we have to do is that we have to unify these guys. And now we might get some recursive problems, but let's try this and see if that works. Oh my, oh my. So no type errors. And here, what the final thing we'll do is that just like we have a pretty printing for P expressions, let's do one for T expressions. And then I think we might be done. Let's just put it here. No, that's wrong because we need the pretty type thing. So, okay, we'll just hack because why not? It's close. So let's do pretty T expression instead. In selection, which one is that? Oh, you have to use this guy, or where is it? In selection. Yeah. replace all. There you go. Okay, and then it's T for everything. And then we gotta add the types a bunch of places. And this one needs an environment to be able to print the type. That's fine. We'll give it a type environment. And the same for this guy. Let's do it like that. Okay, so we'll just say PT like that. That's a function that'll add that thing. Like that. Okay, and then let's do the other ones here. Okay. All the recursive calls. God damn it, there are many of them. I could have done the rec trick. That might have been better. Oh, there you go. All right, so let's export this guy as well. And then let's print it. Pretty T expression of our type environment and that expression, right? So damn, it's hard to read. I guess we need some parentheses or something to figure out what's what. But it looks like there are still some type variables that are not resolved here. So how can I improve it? Which constructs are it? I guess ID, we should have a parenthesis around this one. So we can better see the type. Let's try that. Yeah, so this one doesn't have, and we don't know the type of these guys. That's very surprising. I thought we resolved those guys, so there must be some mistake somewhere because we do have them up here, right? Int. So here we have a var that gives a lambda, but then, well, all right. Did I do everything right here? So one thing we can do is that we can print all the type two vars we have. see what bindings we have for each of them. And we can print what the root is for that particular guy. Union find T environment, union find, type bars. Okay, so that's what did I, yeah, well, I gotta give it the environment. No overlap between type and expression, that's true. Pretty type is not exported. Here is the prototype, we'll export that guy as well. So let's see what happens here. Okay, so when we say A0, there is no type binding for A0, but we don't know if it's unified with something else. So in addition to this map, now one thing I'm a little bit surprised about is that I thought that we cleared out the bindings for those when we merged them. Didn't we do that? Didn't I remove the bindings for those when we have a unification between two vars? Two var against two var. No, we didn't remove them. Okay, so I think we should. So here we should say two vars remove from tree. This guy, we're going to remove that binding because it's going to be moved to the other one. That's the entire point. Okay, so let's try that. And let's see. Okay, now there still is one here, so that's surprising. How can that happen? How can we still have some that are bound in those environments even though they are unified? I guess it's because when we bind a type variable, it might have a different root. Union find environment union find tyvar, and that's the one we should be looking up and using here. Root. So we resolve, what did I do? Oh, it's not root here, it's tyvars here and root here. Okay, so let's try that again. So it still has some that are in the wrong environment, but now let's find out why that is. At least it knew that this if is a bool, so something worked, but we still have some that are wrong. So in addition to printing the type bindings, we could print all the union find bindings. So what we can do is that we can say eta e type environment union find parents. So I know this union find representation has an array with all the parents. That's what this guy does. E parent. And it's a bunch of references. So this is a reference to an integer equivalence classes. If this is less than our next unique ID, this is what we call unique ID, unique, just unique. If it's one of these guys, we're going to print what the root is. Root of is so in fact we can do it like this instead. This is more clear. We don't want to traverse that thing. We'll just go over our IDs. We know how many there are. This is much more clear. Let's do it like that instead. So for each of these guys, we'll find out what is the root of that type variable. Okay, like this. So these are tyvar bindings. And these are equivalence classes down there. And okay, So let's run that. And now we can see 0 it's a root for itself. So what's going on? Most of them are themselves.
Typo. You
I'm
should
sorry?
write
Oh,
root
yeah, I got to print
line.
the root. Yeah, all right. Okay, so 0 is 0. So nothing unified against 0. Okay, so definitely we didn't get the correct equivalence class for 0. So the other thing we're going to do is that we're just going to add a print when we do unification. Union here. Unifying So do we have any unification with 0 at any point? We don't. There is no unification with 0. And 0 is the bar in this call, okay? And if we look at the call here, unifying 19 and 1. Why is it 1? The variable is giving type bar 1. So did we have a mistake in var? Unified types. So this type should be 0, right? Now, but it has 1. So why does it have 1? But down here, it says 0. And 1 is int. Is it a different var? No, it's talking about n. It's not that one. We got to find the oh, it's not. It's in the special case for built-in calls. It's not a var. The call, we had a special case for built-in vars. These guys here, and here we don't unify against this one. That's why. So here we gotta do this thing where we unify this one with the recall type, with the return type. So M type against the convention is to call them T types, but that's already taken. So we'll just call it TV here. Okay. Let's see if that helps. Now, at least this one has a little more progress. A17, so that doesn't have a binding. 17 doesn't have a binding. Okay. So now we can go look for 17. Sequence gave 17. Let gave 17. If we search for 17, unifying 17 and 39, 38. But they don't have a binding, both of them. So this comparison is against n, 17, but why don't we know what n is, right? Don't we? No, we don't. So we never found out what n is. And it should happen down here where we unify multiplication. So why do these have different type bars? They shouldn't. Multiplication should have the same type bar for both type arguments. Okay, so we have a problem there. And let's go and look at the built-ins. Did I make a mistake there, built-in? Oh, it is correct. This int, it is. So that's fine. I'm sorry. I'm confused. But here, the argument against this lambda, this type is int to int to int. That should be matched against the call n to the rest. So call doesn't seem to do the right thing. Let's see. Call arguments should be matched against the arguments, right? So we have fn. We take each of the arguments here. And I think it's because, no, what is the reason? So in this case, we have this guy is, the arguments for the call are n and another expression. And the type of these guys are tyvars, okay. So that's where I guess the tyvar comes from, these guys. But why don't we bind it against TFN here? Why isn't this resulting in unification between these two guys? Bind call to FN, and let's print these guys out to see why they're not unified. Maybe they are, but we just have a bug. All right, I'll give it 5 more minutes and then I think we'll stop, no matter if it works or not, but you know, so binding call here. So we're binding this function call to this function call, and at least we have an int here. But why isn't it? I'm very surprised. This guy should be int to int, right? What call is it the correct call? Maybe this is not the correct call. No, this is the comparison. That's not the right one. So here, okay, here. So here we are unifying int to type 1 nitten, type this guy and this guy. So 19 should be int and 25 should be int. So when we're unifying two functions, something's not working. So this guy unified types for function against function doesn't seem to work. Function against function. Okay. And indeed it is in here. So why doesn't this unification against int and type variable work? It doesn't seem that works, right? Because we are in here and these guys, this unification doesn't work for some reason. So here we should have int against type vars. We do. So int against type var doesn't work. So let's see what could the problem be? If we have a left and we have an int, we do right. And what is do right? If it's a type variable, we swap them. So that will be a type variable against an int. So type variable against something else, and then we bind it. So here we should be binding the type no matter what, right? Binding tyvar against this type. So we should see a binding 17 to int somewhere. We have a lot of binding to int, but they don't seem to work. So let's check one of these guys. Let's see Which one is it? What is the number? 17. Binding. No, but it's never bound. 17 is never bound. Okay, so it must be an equivalence class. What's an equivalence class of 19? A lot of different things are. Okay, so one of the bindings. Let's find the correct call. So let's do a print of the built-in so we have the right place in the print. It's in here. So built-in. Okay, built-in, and we want to have minus as an example here. So binding T to binding 27 to int 28, 26, 27. All right, 27 here, that's an int. Okay, 16. What am I missing? Am I completely going bonkers? Maybe we should do the less than, because that doesn't work either. So let's say binding this guy 0 to binding to type function. But it doesn't, I should add the print for unification of functions again. We had that in a moment ago here. So unifying functions. Unifying functions here. So these two are both type variables. So type var 21 and 23 should be unified. That's correct. And 17 is that type. And 17, why isn't 17 bound to anything? So let's see 17. Okay. So these are strange, right? Because we have 17, but other type vars have int in there. So it's bound in the wrong place. So we know 5 is the same as 27 and 17, but it's an int. But it should have been 17, that's the int. So when we're unifying, it seems we get them stored in the wrong place. Bind to var, I guess, is wrong. Bind to var here. So let's see in root. All right. So let's see.
Maybe we can set both of these, the root and the other, so we can set the tree of type vars both as a resulting type. We are setting only for the root.
Sure, but I want to find out why we don't have. The thing is, it should be correct to only set one of them, and that's why here we go 24. 24 int has root. So what about 24 is wrong? So I want to have a clean data structure, because otherwise it can be obsolete information in some sense. So here 21 is set to int, but that's gonna be done in tyvar number 24. And here we unify 24 and 21, and 21 and 23. And if we look at the var map, 24 has this guy, but it has root 17, which is very surprising. So something inside this guy, I think the way to print this is, it's better to do it the other way around. For each root, print all of those that are inside it. That would be a way to do it. But anyways, I think now it has been 2 hours, and I think that's has to be enough for now. But I hope that the idea is clear. There is definitely a bug somewhere, but I hope that the structure of this type inference makes sense, that you basically unify everything and then calculate what the type should be. And then the union-find data structure can help you make sure that it works correctly. But clearly we have some bug somewhere. But I'll try to find that and then maybe report on it next time what it was. But let's stop it here unless there are any questions at the end. I don't hear any questions.
One question about you used a lot of traverse of syntax tree. Maybe we could write a general function just like a traverse the syntax tree of a program and do some actions. And in this
Sure.
case, you shouldn't write a lot of this boilerplate code for all the, but maybe it is, but it will work only for the easy transformations like resolving typebars.
No, of course, this code is not very clean. We changed it a bunch of times. We have the different conversions on all of that. So obviously, to make production code, you would look at this code when it works, and then figure out how can we clean it up and refactor it. So I would always do that, move things out to separate files, and clean it up afterwards. But to me, a good process is to get it to work first, and then often after that, you can figure out how to clean it up. That's normally how I do it. Because as you could see, we made a mistake. I made a mistake at first by doing the conversion and type checking at the same time. And some of these problems will happen. And that's why you don't want to clean it up before it works, because often you'll throw away out that code or whatever, right? So, but I do agree that this is not, this is not production code. It would take 1 more hour, find the bug and then clean it up. And maybe in 1 more hour, it would be much better. So, but I think it's too much today. 2 hours, that's enough. After all, it's just it's not a real production thing we're doing here. It's just to illustrate some principles about what type of inference is and how it works, and also how I program and debug. All right. If that's it, then I'll say thank you for this time. And we didn't get it to work, but that's okay. That happens. Maybe next time we'll have something that works. Bye for now.
Bye.
Bye.
Thank you.
Bye.